In yesterday's lesson, we talked about direct variation. That's where two variables were directly proportional. As one variable increased, the other variable increased as well. Well, today we get the opposite of that. It's inverse variation. Now we're looking at how two quantities are related inversely. As one variable increases, the other variable is going to decrease. In other words, they're going to kind of move in opposite directions. Now, an inverse variation equation is one that can be modeled by this general form right here. Y equals k divided by x to the nth power. Now, this is a little bit different than our direct variation. Remember, direct variation, we had y equals k times x to the nth. Here you can see our constant of variation is being divided by x to the nth. Now, k still represents a constant of variation, and n is still going to be the power on our independent variable. And just like yesterday, we're going to be able to find the constant of variation if we know one relationship. We're going to take that ordered pair, that relation, and we're going to substitute it into our general format of that inverse variation, and then we're going to solve for k. Let's take a look at example 1. The length of time it takes to travel a certain distance varies inversely with the speed that car is traveling at. Think about it for a minute. You live a certain distance from school. Let's say one day your older sibling drives you to school at a much faster rate than the bus drives you to school. Well, you're going to get there a lot sooner if you drive at a faster rate. So as your rate increased, the time it took you to get to school decreased. We would say t, the time it takes to get to school, is going to be inversely related to the speed at which you're traveling. So t is equal to k divided by s. If you travel at a speed of 44 miles per hour, how far will you have traveled in 3 hours? So here's an example where we are going to find our constant of variation. We have our rate here of 44, which is our independent variable, 44, and our time here, which is our dependent variable of 3. So we're going to substitute that relation in here, and we're going to end up with 3 is equal to k over 44. Now, in order to get that 44 out of the denominator, we're going to multiply both sides by 44. And that means I'll have 3 times 44 is equal to my constant of variation, and that's going to give me 132. All right, let's look at example 2. Again, we want you to get in the habit of thinking about how variables relate to each other. So in this example, we want you to determine whether the two variables represent a direct variation, an inverse variation, or neither. So the first up, we have the intensity of light and the distance from that light source. Again, think about these on the xy plane. If we were to graph this, and typically our first variable is going to be the dependent, and that's going to be our y-axis, the intensity of light, and the distance from that light. So we'll call this distance. So as your distance from that light increases, as you get further and further away from that light, what do you suppose is happening to that intensity? Well, let's just take an example, I guess. The intensity of the sun when you're standing at Mars, which is closer to the sun, would be much more than the intensity of the sun when you're on Earth, which is still much more than the intensity of that light when you're standing on Saturn, which is even further from the sun. So as that distance increases, you can see that that intensity of that sun is going to decrease. So here we're going to say that this is an inverse variation. All right, next up, here's my favorite topic, the diameter of a pizza and the area of that pizza. Well, pizzas come in circles, so I'm going to draw a little bit of a different visual here. Here's a small pizza, here's a medium, and here's an extra large pizza. So that diameter is just that distance across. And you can see that as that diameter increases, the area of that pizza is also going to increase. So when two variables move in that same direction, we call those directly proportional. So this is a direct variation problem. Lastly here, we have the time it takes to walk to your friend's house and your walking speed. So again, let's draw a little axes here. We have time and we have speed. So the time it takes is going to depend on the speed at which you walk at. And this is very similar to our previous example here. So as the speed increases, as you walk at a faster and faster rate, that time it's going to take you is going to decrease. So this is going to be an example of an inverse variation. All right, well, just like we had some steps to work through when solving problems with direct variation in our previous video, we're going to have some similar steps to walk through when solving problems involving inverse variation. And again, these are steps you can exercise to become a mathlete. All right, first up, it's going to look very familiar. Read through the problem, underline the variables that are inversely related this time, and make sure you identify which one's the independent and which one's the dependent. Then you're going to write that general form of the equation, of the variation equation. And remember that general form always takes on y equals k divided by x to the nth. Substitute one known relation in to find the value of k, the constant of variation. Then you're going to rewrite that equation using the constant of variation, and then use that to model, to find solutions for other values of your independent variable. All right, let's get some practice using those steps. Example 3 tells us about the problem of the law of the lever, or the pivot point here. And this goes like this. The distance a person sits from the pivot point of a seesaw is inversely proportional to the weight of that person. Okay, this is known as the law of the lever. It can be expressed using an inverse variation equation, d equals k divided by w, where d is a person's distance in meters and from the pivot point, and w is the person's weight. All right, suppose Carrie weighs 34 kilograms, is 1.8 meters from the pivot. If Madison weighs 38 kilograms, how far from the pivot does she need to sit to balance Carrie? So let's start off by writing our equation. And it's nice that it's already given to us here. The distance from the pivot point is inversely proportional to the weight of that person sitting on the seesaw. They've also already defined our variables. D is the distance a person sits from the pivot, and W is that person's weight. However, they didn't tell us which one is the dependent. And you might already be able to tell this, but your distance is your dependent, and the weight is going to be the independent. All right, so we have our variation equation. Now we're going to use our known relation to find the value of k. Well, we know that Carrie weighs 34 kilograms. She's not that light. 34 kilograms and is 1.8 meters from the pivot. So we're going to substitute those guys in. 1.8 is our distance, k divided by her weight of 34. Now we're going to find that constant of variation by multiplying both sides by 34. And we get 34 times 1.8. Our constant of variation is going to be 61.2. All right, it's important to carry out those decimals, so round to the nearest tenth or hundredth here. Now we're going to rewrite the equation using the constant of variation. So d equals 61.2 divided by w. And now we're finally going to be able to find Madison, the distance that Madison needs to sit in order to balance out her friend, whoever it is, Carrie. There you go. So distance is equal to 61.2. Now we're going to plug in Maddie's weight here, and Maddie is 38 kilograms. So when we take 61.2 divided by 38, we are going to get 1.61 meters. So if Carrie is able to position herself 1.61 meters from that pivot point, they will be in perfect balance. All right, let's take a look at two more examples here. This is one that's going to get us to practice writing that equation. We have y varies inversely as the cube of x. So let's pause there and let's write that equation. Y varies inversely with the cube of x. And I'm going to circle that so I know that it has to be x to the third power. Y is my dependent and x is my independent. If y is 26 when x is 2, there's my one relation that I know. I want to find y when x is 5. All right, so let's substitute that known relation in. 26 is equal to k over 2 cubed. Now we're going to solve for k. Well, 2 cubed is 8. I'm going to do that first. 2 times 2 times 2 is 8, so I'm just going to make that 8. And now I'm going to multiply 8 over to the other side. And that's going to give me a k value of 8 times 26. Let me just check my math here. And that gives me 208. All right, I'm going to rewrite my equation now using my constant of variation. Y equals 208 divided by x cubed. Finally, I want to find the value of y when x is 5. So now we're going to substitute that 5 into our equation. So we get y equals 208 divided by 5 cubed. Well, 5 cubed is 125, so 208 divided by 125 is going to give me 1.664. All right, our final example for today deals with tiling your kitchen floor. We got the number of square tiles, talking about those little square tiles that are on your kitchen floor. It takes to cover a floor varies inversely as the square of the length of the side of the tile. All right, I'm going to pause there and think about our variables. We have t for the number of tiles, and I'm going to say that this is going to be the dependent variable because the number of tiles is going to depend on the size of the tile. The other variable we have is the length of the side of the tile. So that's the edge length. We're going to call that E. All right. And now I'm going to write that inverse variation equation. I see that t varies inversely as the square of that length. So that's k divided by e squared. All right, once I have my inverse variation equation, now I can keep reading. I see that I have 140 12-inch tiles will cover my floor. How many 6-inch tiles will it take to cover that same floor? So step one, let's substitute in our known values. We know 140 is going to be k divided by 12 squared. Well, we need to multiply 12 squared out of the denominator in order to get it over to the other side. So k is going to equal 140 times 12 squared. And that's going to give me a large number, 20,160. All right, that is my constant of variation. Next, I'm going to rewrite my variation equation. T is equal to 20,160 divided by my edge length squared. Now I can use this constant of variation, this equation, to find out the number of tiles I will need if my edge length is 6. So we're going to plug 6 in for E. So the number of tiles is equal to 20,160 divided by 6 squared, which gives me 36. And when I take 20,160 divided by 36, I'm going to end up with 560 tiles.